complexification is the formal name for something that you did in your previous linear algebra class with a lot of hand waving. And it basically works like this. Remember if you had some matrix A, some n by n matrix A, and you were looking for eigenvalues, and you said, oh, you know what? There are no eigenvalues for this matrix, or we end up with some irreducible quadratic or something like that, and then you're all sad and you have no eigenvalues or eigenvectors. And then your teacher says, hey, wait, that's just because you were assuming that U was an element of Rn, which is what any normal human being would do. But forget about that, because we could suppose that U was actually an element of Cn. And even though A is a matrix with all real valued entries, it still defines a perfectly a perfectly valid transformation. So if we say T of U equals A times U, you start off thinking that this is giving you a transform from Rn to Rn, but you could just as easily think of it as giving you a transformation from Cn to Cn, because in order for those that matrix product AU to be well defined, you just have to make sure that the lengths of the vector and the size of the matrix are compatible. So you just say, oh, okay, you know what? Forget about it. Now we're supposing that U is allowed to take complex entries, and lambda can now be a complex number, and then we can find all the eigenvalues and eigenvectors we need, and we can be happy and go on and play all of our reindeer games, right? Okay, well, complexification is the formal name for that process. So let's see. So if V is a real vector space, and the real part's kind of important because otherwise you wouldn't bother complexifying it because it would already be complex. We can define its complexification and this will be denoted by V with a superscript C for the complex. And it's actually just a Cartesian product of V with itself, so it mimics the construction of the complex numbers from the reals. And we write a vector U comma V as U plus IV. Okay, and so that's what an element of VC looks like. And so the key point here is that a vector, so you can have a vector U, which is equal to U plus 0I, and this is considered now as being an element of V cross V, or as we now call it VC, where the second coordinate is just equal to 0. But if I multiply by the scalar I, then I end up with IU, which is 0 plus IU, which is still in VC, but now it has the first coordinate equal to 0. So the key point is that it's possible to take something in V cross 0, which is a subset of, or a subspace of VC, and by multiplying by the appropriate scalar, you end up with something that's in 0 cross V. So that scalar multiplication can kind of take you from one coordinate to the next, which is the funky thing that allows this to work. So, and it has some perhaps unexpected consequences. So first, let me just write down, we're going to think of V as a subspace of VC by identifying an element of V with u plus 0I. And that's exactly what we do with real numbers, right? We think of the real numbers as a subfield of the complex numbers. Okay, and so now, for example, if V1 through Vn is a basis of V, then let's see, how do we get a basis of VC? Well, your first thought might be to say, okay, so let's take these and then let's take them multiplied by I, so we have stuff that goes in the second slot, right? And then you realize, oh wait, that's actually just a scalar multiple of the things we already had in our basis, so we don't need those. We've already got them in our basis, and so what do we need for our basis? Well, nothing. We've already got one. So a basis for V is also a basis for the complexification of V, because for the complexification you're allowed to have complex scalars, and that allows you to sort of take those basis vectors wherever you need them to be. And so along with the complexification of V, we can also complexify an operator. So complexification. So the complexification of an operator T on V is denoted T sub C, and now this is an operator on V sub C, and it's defined by saying that the way we define it on one of these complexified vectors is it's going to be T of U plus I T of V. And so in this definition, we've broken it down into, in terms of T, which we understand because we're given that at the outset, and T's action on V, which is where T is defined to be an operator. So that's a well-defined definition. And so this is exactly what we do when we consider a real valued matrix as something that we can multiply against some complex vector, right? So it's a real valued guy doing its real valued job on a complex valued thingy, and it just does it component wise like we do everything in a linear algebra class.